let's proceed. There are some technical problems, but after the first two talks, we will change the system. For the time being, we have made some temporary arrangements. So let's continue. So to understand the soft matter, why it is soft, we need to look into the amount of energy which it takes to remove a building block of the material. So that assessment is going to give an idea why a soft matter is called a soft matter. Now, the more energy you need to remove a building block from a compound or from a material, the more solid-like behavior it will show. Less amount of energy you require to remove a constituent of an object, more soft it will appear. So what we are going to define the softness of a material is in terms of the energy as well as modulus. Okay, so we are going to show why KBT, actually the room temperature thermal energy, KBT at room temperature, is the key yardstick actually to understand whether something is soft or hard. Okay, so soft matter, I told you that the energy which is associated with the thermal energy, so the KBT is say of the order of 4.1 into 10 to power minus 21 joule at temperature T is equal to 298 Kelvin. So this is the amount of energy which is there when the temperature is 298 Kelvin. Now, the energy which is required to disturb, okay, a single component of a soft matter is broadly of the order of 1 to 10 joule, or I should say 1 to 10, not joule, 1 to say KBT, 1 to 10 KBT. So you can understand that the energy which is present at the temperature 2 thermal energy with the temperature 298 Kelvin is 4.1 into 10 minus 21 joule. The energy, the on average energy which is required to deform a soft matter is of the order of 1 to 10 kBT. So the point is that if the energy required to modify the shape of an object is in the unit of kBT or in some lumps of kBT, then thermal energy will be sufficient, okay, to disturb the shape or structure of a material, and then the material is called soft. Okay, so broad class of material. So let me move on to the next one. So this the interaction energies of mesoscopic constituent is of the order of kBT, and associated shear modulus as well as Young moduli are smaller, much smaller than the crystalline solid, and therefore the free energy, okay, of a soft material is dominated by the entropy. Okay, and that's why you will find that the shape of a soft matter is mostly distorted most of the time. For that you have to make the temperature so strong that interaction energy starts playing a significant role, so that you can get an ordered structure. So this slide tells us that that soft matter is actually an interdisciplinary area of physics, materials, engineering, AI, ML, biology, chemistry, everything comes into the pictures. So colloids is one kind of soft matter which is made up of tiny particles which are suspended in the mediums. Then granular medias like sand, powder, and grains. Then there is another example, foam. So dispersion of gas in a liquid or solid, such as shaving foam or such kind of object like froth on beer. Then the polymers, for those who are working in biological materials, they must be aware that all the biological molecules are soft. Then comes the non-Newtonian fluids, like a mixture of corn starch and water is another example of non-Newtonian fluid, whose viscosity actually changes with applied stress or strain. Then rheology, the study of flow and deformations, which is central to the understanding of how soft material behaves under stress. Then comes the active matter, which are example of materials where individual units consume energy from its surroundings, okay, to move or create structures. So these are the examples, broad examples of materials which are classified as soft materials, and the matter about which we are concerned is the active matter. We will discuss about it later. Now, in order to proceed, when we see matters around us, we can classify two different kind of objects from the point of view of they are moving or not. Okay. So, and if they are moving, what kind of force is actually driving them, okay, to a certain kind of certain direction. So driven systems, when I say driven systems in physics, is a system in which energy is continuously supplied by an external force or influence. Okay. So for example, a car which is moving, the energy is coming from burning the fuel. Okay. We are putting a metal bar in a hot oven. Okay. Therefore, we are supplying heat energy at one end, and we see that the heat, there is a temperature gradient which comes into the picture from one end to the other end, which is quite natural. So the definition is a driven system in physics is a system in which energy is continuously supplied by an external force or influence, maintaining its motion or dynamics beyond what would occur naturally or in isolation. Means if it is in isolation, nothing is going to happen. But if some external force is applied, then it starts showing some sort of directed movement. Okay. So as soon as you provide energy continuously from outside, such systems starts showing some sort of fluxes. Fluxes in the sense that if you talk about the system of gases, then there will be a net flux of number of particles which are moving from one side to another side. In the case of rods, iron rods kept in contact with a oven, there is a flow of heat, okay, from one side to the other side. So that flux, energy flux, is coming into the picture. And then such systems are classified into the non-equilibrium system, but non-equilibrium steady states. Non-equilibrium means if you are seeing that there is a temperature gradient when you put a metal bar in the contact of an oven, but the temperature gradient, okay, is maintained and doesn't change with time. After certain time, it will become stable. So there is a continuous supply of heat, okay, and there is an equilibrium between the environment and the bar. So the temperature gradient is maintained, heat is being supplied. Okay, so this is an example of a non-equilibrium system, but non-equilibrium is steady state. Okay. So I will tell about the non-equilibrium steady state or steady state later. So these are the examples which I have shown here: biological systems, some artificial systems like molecular motors, or you can say the seared colloids, second granular layers. If you have some solution, you shake it, it become okay. So, and if you keep on shaking it at a continuous frequency or speed, it will get a definite structure which will remain there in the medium. Then the motor driven cytoskeletal filaments, catalytic Janus particles, all these are the examples of some driven systems. Now, active matter and driven systems. So when I told in the beginning about the active matter, I also told that we are supplying some sort of energy is being consumed, and there is a directed motion. There is a motion in that. So from driven system, now we are shifting to the active matter, and I will tell you what is the difference between the two. Okay, not all driven systems are active matters. Okay, so when we talk about the active matters are driven systems in which energy is supplied directly, isotropically, and independently at the level of individual constituents. Okay, individual constituents which are active matter. And in dissipating it, they generate systematic motion. Okay, so in other words, sometimes people say that the energy, the active particles, they take energy from its surrounding, okay, and they behave independently, and in the process they exhibit structures as well as some sort of directed motion. Okay, so now we are talking about the supply of energy at the constituent level, not at the bulk level. So in the earlier case, it was the situation of a bulk material to which we are supplying the heat. Okay, so this is the definition. Now in this particular case, since it is a non-equilibrium systems, the detailed balance about which we will discuss later on, detailed balance is broken down. These materials, they exhibit collective behaviors, self-organization, and non-equilibrium phases, okay, over a period of time. Now, what are the examples? Examples I have already given. Some bacterial colonies, Janus particles, colloidal particles, self-propelled colloids. Some of the pictures are familiar. So that is the locust. I think the picture of a locust moving from one part of space to another part. They exhibit directed motion. Now you see, in the movement of such bodies, okay, each and every individual locust is independent, okay, but in some way they are getting into a pattern. Okay, they are independent, they can take their own decision. Okay, so they are consuming their own energy, they are burning their own energy. If they will burn their entire energy, they will die. They are not going to be helped by any other locust. So such an examples are there.
This breaking detail balance is taking it that it's equivalent to breaking symmetry, which is what kind of order I should.
Detail, but no, I don't think that breaking symmetry happens in equilibrium also. Okay, but detail balance is always there. Okay, breaking symmetry means is some sort of ordering is being created. So that happens in both the situations.
Still, once in 10 minutes, we study it is the financial example. That's so better than getting a instead. It's the complete thing. Martha is all I'm getting what we're going on is.
No, detailed balance is actually a different concept, which is related with whether the system is in equilibrium or not. Say, if there is a process, okay, which is happening, okay, and if the process in the forward direction is balanced by the process in the reverse direction, that is called the detailed balance. Okay, that is solely a property of equilibrium processes. All equilibrium process, at equilibrium this happens. Detailed balance is maintained. Okay, as soon as you go into a situation where there is non-equilibrium is coming into picture, detailed balance is completely broken. So suppose if you know the statistical mechanics, there is a probability of a statistical system to go into a particular configuration or to a microstate. Okay, right? And then that system can make a transition from one particular kind of microstate to another kind of microstate. You got a point? So if the situation is such that the forward one-way direction of the transition is balanced by the reverse direction, then there is a equilibrium. So you know the equilibrium happens in all sorts of, let's say for example, water boiling. Okay, so vapor is coming out of it. Okay, so after certain time, because of the environmental pressure, you get a equilibrium situation that the amount of water which is going into the vapor phase becomes equal to the amount of vapor molecules being converting into the liquid. So that is the equilibrium. So the forward process is being balanced by the reverse process. Okay, then that condition is called the equilibrium condition, that we ensure whenever you perform the simulation. Okay, you got a point? Right. So you got the answer of your question or not? Right? So you talked about the magnetic system. So if the magnetic system is in a transient state, time, so it's a non-equilibrium state, then detailed balance condition will not be satisfied. Okay, once it is in equilibrium, what does it mean? That the spins, because of the thermal fluctuations, some of the spins are being oriented, okay, to create a paramagnetic salt. However, there are some other molecules, they will get into the random direction. So the overall equilibrium is maintained. Okay, so now what is the motivation of this lecture? The lecture is that the statistical mechanics basically provides the baseline. Okay, it also leads us from equilibrium, that is the passive cases, to the non-equilibrium, which are active cases. Okay, so that's why we are discussing this particular part. Now the question is, what is statistical physics? So I'm taught by Professor Yashwant Singh sir. Right. So it's always difficult to talk about the subject in front of your teacher, actually. But it's very nice that he can correct us at any time. Now, statistical physics consists of study of special laws, okay, which are required to deal with the systems which are macroscopic in size. Okay, when I'm saying macroscopic in size, I mean systems made up of large number of constituent particles. Okay, now this particular subject, it asserts that if you know the property of the macroscopic constituents and how they interact with each other, okay, then we can predict about its macroscopy. So if you know there's a misprinting, if you know the microscopic, okay, constituent, properties of the microscopic constituents and how they interact with each other, then we can always make prediction about its macroscopic behavior. Okay, so if you know, say for example, if you have a gas, hydrogen gas filled in a jar, you know that the gases of hydrogen, how they are interacting. It says that by using the rules, okay, of statistical mechanics, we can predict all the observable properties. Say for example, pressure. We can calculate temperature. We can calculate specific heat. Okay, all those properties can be calculated using the laws of statistical mechanics, which is basically based on averaging. Okay, so average or the mean, taking mean is something is at the heart of the statistical mechanics. Okay, because we know, say if you talk about the pressure, what is pressure? The molecules or the particles of the gas, they are continuously in motion, and in that process they are colliding with the wall, so they are applying some impact, some force. Okay, so you can calculate the change in momentum whenever they are colliding and reflecting. With that change in momentum, you can calculate the force, and then the force per unit area is pressure. So if you can understand this thing as if you know this particular contribution which are coming from each and every individual particle of the gas. Okay, then by summing over all the contributions of the constituent particles and taking the average of it, you will be able to calculate the pressure. Okay, that's how thermodynamically it works. Similarly, temperature is what? It's the average kinetic energy. Okay, measure of the averaged kinetic energy of the constituent particles. So everything is now the concept which lies behind the statistical mechanics, how it applies, how to get into the job to calculating the property. It has something inherently built into it, that there are two things. There should be two things which are needed. First, that the system should be large in size. When I'm saying large in size, it simply means we are talking about thermodynamic limit. Okay, thermodynamic limit means we are talking about the number of particles to be very large. Okay, so volume is also tends to infinity, so that keeping n by v constant. So if you work in this particular limit, n by v constant means what? Number density is constant, fixed. Okay, so if this is the situation, then we say that we are in the thermodynamic limit. Okay, in that particular condition, statistical mechanics predict properties up to a very high level of accuracy. Okay, now I am saying that it predicts the property. Okay, because statistical mechanics doesn't give, like quantum mechanics, it doesn't give definitive answer. Okay, it also talks about the properties which are most probable. Okay, so probability is inbuilt into the statistical mechanics also, like quantum mechanics. Why? Probability comes into picture. Suppose you know your friend, okay, on the first day, and someone asks you about where he will be found at a particular time. You will not be able to tell because you don't have enough information about him. But after an entire semester, you know his routine, and you will be able to predict where he will be found at a particular point of time of a day. But this particular thing, okay, is that you don't know the information. Okay, here in this particular case, when we talk about the statistical system, okay, we don't know. Actually, our previous knowledge tells us that if you want to calculate the properties of a system, why we are going to formulate a new set of rules? We already know classical mechanics. Okay, we can solve Newtonian equation of motion, or if the quantum particles are there, then you can solve Schrodinger wave equations. But you know, solving Newtonian equations for one particles is okay. We are habitual of doing it. But as soon as you go for two particle case, it becomes very difficult. It's a set of differential equations. Okay, so complications enter into picture. Can you think of solving three particle system? It's very, very difficult. It's a, and then you are talking about a system which is in which n is actually very large. N is large means n is of the Avogadro number. Okay, then it's a hopeless situation. Okay, because we, even if you can write the Newtonian equation of motion or the Schrödinger equation of motion, you don't know the initial conditions. You will not be able to solve it accurately. So this knowledge, lack of knowledge, reflects into the probabilistic nature of the property. So we always calculate average and the most probable probability of finding a system in a particular state. All these terms we use, okay, because we don't know about the system. Whenever you don't know, you cannot answer definitely. Okay, so I'm concerned about the equilibrium situations where this statistical law, probabilistic law enters into the picture. Try to imagine when you start talking about the non-equilibrium systems, how much complicated it is going to be. Okay, but statistical mechanics gives us tools to deal with such situations. Okay, so now most important thing is that at this point I should tell you that what is a macroscopic object and what is a microscopic. Macroscopic and microscopic. So you know the macroscopic is the something which is made up of large number of particles, and each and every constituent particle is called microscopic constituent. Okay. Now when something is called macroscopic and something is called microscopic, it depends on the object under study and the properties with which we are concerned. Suppose you talk about a human body. Okay, for human body, okay, if you talk about the temperature of a human body, okay, or if you are talking about the blood circulation, okay, or certain other such kind of properties, you are talking about, say for example, blood pressure, then the blood and other things, the molecules of blood, the water molecules and everything else, that those are the constituent microscopic constituents of the body. Okay, and the body itself is macroscopic. But if we're trying to study about a human society, okay, so where you have a large number of people, like for example, if you talk about the locust, huge, okay, large number of locust flying, or the fishes which are swimming in the river. So for that particular body, each fish or each human being is a microscopic object, and the entire system is macroscopic. The nation is macroscopic. Okay, so it depends upon what kind of thing you are talking about. Okay, so water molecule. Water itself is macroscopic. The water molecules are microscopic. Okay, but to talk about some polymeric molecules, then the polymer itself is macroscopic, and its atom and the molecules, the monomers, becomes microscopic. Okay, so it depends upon. So which of the constituent is called macroscopic, which is called microscopic, it depends upon the context. But so now, how we represent microstate and macrostate of a statistical system? Now, when I talk about the microstate, I simply means to say the most detailed information about the system. Most details means you have to talk about the state of each and every constituent particle of the system. Say for example, in this class, there are 30 students. If I give the information of the seat number of each and every student, then this is the microstate representation. But if you talk about the macrostate, that is the observable property of the system on a whole. Okay, say for example, in the case of gaseous molecule filled in the jar, temperature is a macroscopic observable. Okay, now you always know that the gas molecules are you yourself in a class, right, keeps on changing your positions every day. It is not that today you are sitting here, tomorrow also you will sit here. So the configuration of a system keeps on changing. Okay. However, it may happen that you get the same macroscopic observable. Okay. So for a given macroscopic observable, there are many different microscopic or the micro states which are possible. Okay. For many different micro states, same macro state. So एक ही टेम्परेचर के लिए बहुत सारे अरेंजमेंट हो सकते हैं. Okay. So that number of micro state corresponding to a macro state is called the weight of a macro state. Okay. We represent that by a symbol which is called omega. Okay. Omega. This omega, that is the number of micro state accessible to a system, depends upon various parameters. Okay. It depends upon temperature, volume, okay, number of particles. You can talk about the energy. So it depends upon what kind of system you are taking. Okay. So all these parameters decides that what kind of on what factors this number of microstate accessible to a system depends. Now, here are some examples which I have made for you. See, there is a molecule made up of 4 monomers. This is polymer. Okay. There are various arrangements which are possible. In one particular arrangement, if you take the molecules like this, you get one particular energy value associated. Say, for example, if you talk about this is a 4-particle system. Okay, this is a 4-particle system, and each particle in one particular each particle say contribute. If it is +1 side 1, and if it is minus side -1. Okay, then these are 4 different configurations which contributes to one particular value of total energy, and this particular configuration contributes a different energy value. Okay, but the particle, the system on its own can take any of the configuration independent of the other. So they are all the microstates are equally likely, no preference. Okay, no preference. For example, in this class, if you don't know each other, you can sit with anyone. But tomorrow you develop friendships, then you start sitting with someone. So we are talking about a situation where we don't know anyone. Okay, so all the configurations are equally likely. कोई किसी के साथ बैठे, कोई फर्क नहीं पड़ता, उसको कोई benefit नहीं होने वाला है. Okay. Now here I have tabulated the various configuration of a 2-state system. Okay, 2-state system means a particle which can take up, which can point in a up direction or down direction. Okay, with respect to externally applied magnetic field, and the corresponding magnetic moment and energy is also listed here. I don't know whether it is visible or not. But you can see that the first particular way of arranging all the particles may be that all the particles are in the up state. They're in the up state, so that their magnetic moments happen to be 4 mu naught, and if they are placed in the magnetic field, then energy is -4 mu naught B. Okay, -4 mu naught B. This if all are in the up state. 2 state का हमारा केस है, या तो ऐसे रहेगा या ऐसे रहेगा with respect to a magnetic fields, and we have 4 particles. Okay, so if all the particles are in the up state, that is parallel to the magnetic field, then this is then the second possibility is that 3 are up, 1 down, so the energy is -2 mu naught B. Second is that again not this one but this one is down, so there are 4 possibilities in which one particular particle is in down. Okay, and then you start filling it with the 2 down, 2 up. So you can see that there are various possibilities where you have 2 up and 2 down. Okay, and then corresponding to which, since 2 up and 2 down means the moment is 0 and the energy will also be 0. So see, if the system is in such a situation where 2 up and 2 down, and you make an observation, you will get 0 energy values. We say the system is in the zero level. Okay. Similarly, you can come down and you can change the trend. Instead of 3 up, 1 down, 3 down, 1 up. So you have the energy with plus sign. Okay. So you see, this is one macroscopic observable. Okay. So the energy value, okay, 0 is one macroscopic observable value of the macroscopic variables. Macroscopic variable is the energy, corresponding to which we have 1, 2, 3, 4, 5, 6 different possible configurations. So one corresponding to 0 energy value, we have 4 microstate accessible to the system. Okay. Now if you go up, you will see that for the case of -2 mu naught B, there are 4 possibilities of arranging the particles, and plus 2 mu naught B, we have 4 possibilities, and there are just one possibility for -4 mu naught B, where all the particles are up, and one possibility for all the particles being down. Okay, so you can understand that corresponding to a macro state, there may be many possible micro states. Okay, now you can understand that if you sum it, okay, in the system, the particles are changing their direction up down continuously. Okay, but they will fall in one of these conditions only. Okay, so if you sum it and make its average, what is the observable's value which is most probable? So see, the probability is calculated by probability of getting a particular macroscopic value of the observable is written as number of microstate, okay, of our interest, okay, divided by total number of all possibilities. So in this particular case, say for example, this one, 0 value, there are 1, 2, 3, 4, 5, 6, and total values are 16. So 6 divided by 16 is the probability to get the value of energy 0. Okay, but since there are 4 possibilities for -2 mu naught B, so the probability of getting it is 4, okay, divided by 16, 1 by 4. Probability of getting -4 mu naught is 1 by 16. Okay, so the most probable one is 0. Okay, so this is a very small system where we have just 4 particles. If you take large system where number of particles is huge, Avogadro number size, then at equilibrium, what happens that the system always get into that particular macro state, corresponding to which my number of micro state is maximum. Number of micro state means in that particular configuration, system spends most of its time. Okay, most of its time. So that's how we get the that's why we try to understand how the statistical mechanics develops. Okay, how we calculate the properties. Okay, so let's move on. I think it's bolo.
Well, if the empty number of particles, how can we on the maximum number of microstates? Because eternal each mark come the ones.
We can actually see इस तरह से picture बनाकर तो नहीं कर पाएंगे, पक्की बात है हम, है ना, we cannot do this, but we can do up to say 8, 16 करके देख सकते हैं आप. But in theory we don't have to actually count each and everything. Okay, we can write down, okay, the probability of a particular occurrence, okay, and then we can occurrence with respect to a number of the probability with respect to the number of as a function of variables. Okay, the variables, suppose we talk about an oscillator system, the variables are energy, number of particle, and volume. Okay, and we can mathematically maximize it.
I know.
Okay, maximize it that for what particular specific values of the variables, okay, we are going to get maximum probability. Okay, so that now from this example we understand that particular macroscopic variable which is most probable, corresponding to which there will be maximum number of microstates. ये हम समझ सकते हैं इसको इस तरीके से. You try to understand? You got my point?
What?
Okay. So then comes the concept of ensemble. What is an ensemble? An ensemble is an arbitrarily large collection of macroscopically identical systems. So we talk about a mental copies of statistical system, okay, which are considered of existing simultaneously, okay, and all those macroscopic copies they correspond to the same macro state but are in all different possible micro states. Okay, say for example, जो पिछला example अभी दिखाया मैंने, in this particular case we talk about that all
Yes.
okay, so all these 6 configurations, okay, they are, now we are considering that we have 4 systems, a system of 4 particles, okay, they are existing together but all possible microstates are lying side by side. One point. तो वैसे ही हुआ जैसे हमारे गैसियस मॉलिक्यूल्स हैं, अगर वो मूव कर रहे हैं, so at every second you take a flash, okay, so one particular configuration you are getting, you can calculate the properties associated with that, but then at the next moment the configuration will change immediately. So that is the second microstate, okay, microscopic state. Okay, fine. Okay, so you already know about all these things that there are 3 different kind of ensembles we talk about: microcanonical ensemble, canonical, and grand canonical. What does it mean? What does it mean means, I will tell just this thing and then we will finish. Suppose we have a system, okay, this is a very large system, okay, this is a very large system having infinite number of particles, okay, and now you want to calculate the property of a subsystem, okay, subsystem which is part of this, the whole part of this system is isolated, and our objective is to calculate the property of this system, system A, okay. Now system A, which is a box, consists infinite number of particles in and so on. So it's also macroscopic system. Okay, large number of particles are there. You got a point?
See.
Now, if you are considering the system, you have to calculate the property of the system. Okay, your objective is to calculate the property of this particular system, which is part of a bigger system. Okay, now how the system's property will come into picture? The easiest thing is that the system is allowed to interact with surrounding, okay?
Yeah.
But as soon as something starts interacting with someone, the entire behavior becomes complicated. Okay, a single human being is always very happy. As soon as he get married, lives become hell. Okay, so they start interacting and the day-to-day life depends upon each other. Okay, if this is the situation, then becomes very difficult. So what is the natural processor, natural way of understanding it? So people, physicists at least, they start making models of Bohr's atomic model, which is a celestial model, okay, solar cell जैसा, and then start taking lots of complication into it. Okay. Here in this case also, people will start by considering this system as an isolated system. Means the particles in this subsystem, they are not allowed to go out, or they are not allowed to take energy or give energy to the outer system. So this is an isolated system. Okay. So if you consider this particular system, then this is the most simple situation. Okay. Particles are not interacting with anybody. मरे हुए पड़े हैं उसमें. Okay. Now, if you are considering such a system, in this particular case, number of particle n, volume and energy, all these are fixed. Then it is called the microcanonical ensemble. And in that particular case, you calculate the total number of microstate accessible to system and total number of microstate accessible to system, okay, is a statistical quantity, and it is connected to thermodynamics by the relation S is equal to K log omega. Okay, so this is how you get the thermodynamics into picture. The next relaxation is that we allow the system, okay, to make it more realistic, we allow the system to exchange energy. Say in this jar, you see, this jar is the same jar as this one, but we have a insulation on the outer wall. So it is not in contact with the external world. But now this insulation has been removed, so it can transfer the heat through the wall to the environment. But number of particles is not changing. If this is the situation, then at equilibrium, we have temperature T, volume, and number of particles fixed. This defines the canonical ensemble. And the next one is, खोल दीजिए इसको. जैसे फॉर एग्जांपल हमने इस वाले एग्जांपल में देखें, तो अभी मैंने होल्स कर दिया. अब हम इसको पूरी तरह से पोरस बना दें, या हम इमेजिनरी बॉक्स कैलकुलेट करें, राइट? So that becomes most realistic situation. Then we get grand canonical ensemble case. Okay, and in that particular case, there are two type of motion. One, number of the particles from this subsystem can go to the bigger system, or particles can come from outer system to the inner system. So both the flow is because open, as well as particles are interacting with the rest of the world. So energy exchange is also possible. Okay. So when equilibrium is reached, okay, the energy flow will stop, or the net flow of energy will stop. And when equilibrium in the sense of number of particle transfer is reached, net flow of particles will also stop. So what are the properties, okay, which dictate? So at equilibrium, temperature of the subsystem become the temperature of the bigger system or the rest of the world, जिसको हम reservoir भी कहते हैं कभी कभी. Temperature and number of particle is actually the flow of number of particle is dictated by a property which is called chemical potential, mu. Okay, so as soon as the chemical potential of the subsystem become equal to the chemical potential of the reservoir, there will be no net flow of particles. Okay, so in this case, the parameters which define the macro state is chemical potential mu, temperature T, and volume V. Okay, no more NEV kind of thing. Okay, so this is how. Okay, so last thing, I think time is up mostly. So this is how the partition function is needed. Partition function is so for example, in the case of microcanonical ensemble, the statistics gives a quantity which is called omega. It is the number of microstate accessible system, which connects the statistics to the thermodynamics. S is equal to K log omega. The same thing is achieved in microcanonical ensemble, in the canonical ensemble through a quantity which is called partition function. Okay, partition function is simply defined as, in the case of canonical ensemble, we write it Z is equal to summation exponential minus beta E n. Okay, Z is equal to summation exponential. What is exponential minus beta En? Exponential minus beta En is called the Boltzmann factor. Okay, Boltzmann factor in a way is called the weight of a particular energy level. Okay, En, weight of a particular. So weight is calculated exponential minus beta En. More the weight, it is highly likely that the system will go into that particular state. Okay, so how to define my partition function? Partition function is the sum of the Boltzmann factors, okay, of the accessible states. Okay, this is how we define and through this we calculate the thermodynamic property through the relation minus kBT log of Z. Okay, so this gives us one-to-one relationship. Now, in the case of microcanonical ensemble, entropy is the quantity which was there from thermodynamics. Entropy has a particular property that it always increases or remain zero. Okay, this is the direction given by the second law of the thermodynamics. Okay, in the same way, for the case of canonical and grand canonical ensemble, okay, this quantity F, that is the Helmholtz energy in this particular case, it always decreases or remains zero. So at equilibrium, if the system is isolated, we talk about the maximization of entropy.
Sure.
Okay, in the same way, if you talk about the canonical system, okay, we talk about the minimization of the Helmholtz energy. So at equilibrium, it becomes minimum. Similar way, in the case of grand canonical ensemble, we talk about the grand potential phi, okay, which is again related by minus kBT log of the corresponding partition function. Let us write it by capital Q. So I will skip all these things. I want to talk about this one also. Okay, pair coalition function. So I wanted to talk about this one, steady state and non-steady state, then I will finish. Okay, because this is going to be very important here. Steady state means that the macroscopic properties of the system, say for example density, velocity, temperature, pressure, etc., do not change. So if the properties of a system become time independent, then we say that we are in a steady state. Okay, steady state can happen both in equilibrium and non-equilibrium. Okay, so if you look at the system now and again later, the large scale averages remains the same. Okay, property remains the same. Okay, so it does not require the system to be in equilibrium. It only requires time independent of those observables. That's all. Okay. Now, a system is in equilibrium when there are no net flux of matter, momentum, or energy. See, this is try to be very specific. We are talking about no net flow. Okay. So, we are talking about, whenever we are talking about equilibrium, we are saying that no net flow of whatever is there to disturb it. Okay. So no net flux of matter, momentum, energy, and all microscopic states follow detailed balance in this particular case. Okay. So in such a state, entropy production is zero. In equilibrium, all microscopic states follow detailed balance. This is the core concept. Okay. Now talks about the non-equilibrium. So when we talk about the non-equilibrium state, okay, which is driven by some sort of force, driving force, okay, there used to be a flux. Some flux will always be there. Okay, say for example heat flow, particle current, chemical reactions, all sorts of things will be there. So net flux will always be there whenever we talk about the non-equilibrium situation. Okay, so entropy in this particular case is being produced and dissipated continuously, and detailed balance is absent in this particular case. Okay, now we talk about the non-equilibrium steady state. Macroscopic observables are again stationary in time के साथ change नहीं करेगा. Okay, but there is a net flow of heat. जैसे for example we gave an example of a heat conduction in rod. Okay, so after certain time the heat is flowing, but the temperature gradient becomes same. It doesn't change with time. Okay, then that is called the non-equilibrium steady state. Okay, so energy or matter is constantly supplied and removed so that the system does not relax to equilibrium. It never relax. Otherwise, if you stop supplying it, okay, it ultimately goes into a situation where detailed balance condition is satisfied. So from a detailed balance absent case, it goes into a detailed balance case. Okay, so these are some of the definitions which I wanted to tell you, but I think I have taken lots of time. Autocorrelation function. Okay, so simply I can just tell you the definition. So if you take any variable, okay, any time dependent variable, the autocorrelation function is defined as its value at a particular time, okay, multiplied the value of the same function after a certain amount of time and take its ensemble average. Okay, so you can take the average over time, or you can take the average over ensemble, or both. These two things comes into picture. And what information they gives? They actually tells us the coherence between or the relations between the values, how the parameter is changing spatially or in time. Okay, so spatially के लिए हम लोगों ने जो correlation function define किया था वो पीछे वाला, अभी हम लोग we are talking about the time. So how the system is decaying with time, or changing with time, or remaining constant with time. Okay, one particular example is, so instead of any variable, you can take the velocity as a variable at a particular time. So the CVT, that is the autocorrelation function, velocity autocorrelation function, we say it, CVT, is the ensemble average of the velocity at time t multiplied the velocity at a certain interval of time tau. Okay, and it tells us about the memory of particle motion. Okay, if CVT is positive, motion is correlated, rapidly decay signal, random movements, all sorts of things it gives, we can decide. Not only that, this velocity autocorrelation function is also related with the self-diffusion coefficient via a particular relation which is called Green's-Kubo relationship. Okay, so I think all these things will be covered by. So, and these are the conditions, detailed conditions for the detailed balance. You see here we are talking about this Pi Wij, where P is the probability of going into a state I, and Wi to j is the transition rate. So transition with the probability of the forward transition is equal to the probability of the backward transition, j to I. Okay, this is the detailed balance condition. The difference of these two is called the current and dissipation. If this ji to j is 0, then we say that the detailed balance condition is satisfied. If it is non-zero, then we have a persistent current and we are into a non-equilibrium situation. Okay, so okay, fine. So I think from here, I think piche nahi ja raha hai. Anyway, so Professor Peng will take us from this discussion of passive particles mostly to the active case using the statistical rules. Okay, so thank you very much. If you have any question, please go ahead. See, the statistical mechanics is a huge subject. It's very, very difficult to cover it in one lecture. Okay, it's always very difficult. Lots of things are there, but I just gave you some of the things which are important. I could not discuss the one particle and two particle density functions, which are very important in order to study the structure of the systems. Okay, and the pair coordination function defined through that. So these materials will be available to you. Okay, and you will be able to learn from it. So now, if you have any question, please go ahead.
I have two questions. So thank you for the very nice lecture. Course, I kind of forgot the basis I was helpful. So
my objective was only that. I was not interested in going into the lots of details actually. Yeah.
So, now one question is that you discussed a bit of air polish, the auto polish functions at the end. Are velocity or the auto polish functions preferred over the usual auto polish function which are
It depends upon the it depends upon the use. Mostly in signal processing, okay, people talk about different kind of autocorrelation. So you can talk about the autocorrelation function of anything. Okay, you just have to choose the variables, okay, which are time dependent. Okay, then you can discuss about the how those variables are evolving with time.
because
It depends. Okay,
it depends.
the context. It depends the context. For example, these people will talk about the velocity autocorrelation functions.
Yeah.
Okay.
Another question is that it might be very nice, but so when we discussed that for equilibrium, the system chooses the macro state, which goes the number of microstates as
In equilibrium. Yes.
And then also another thing that happens in equilibrium is that the Bohr-City theorem that
Yeah. Ergodicity is another requirement.
requirement for
Yeah.
So I was wondering how do we connect these two concepts physically in the sense that I'm going for a microstate into which maximum number of
So ergodicity simply means, okay, that if you just picture in your mind the phase space, and in phase space, okay, the microstate of a system, statistical system, is represented by a point. Okay, you got a point?
Yeah.
So they are represented by a point. So if you just try to imagine about the ensemble, okay, then in the phase space it is going to be a situation of a huge number of points at one time. Okay, so when time evolves, okay, each and every now these phase points, okay, although they are points, their coordinates are the positions and momenta of each and every particle of the constituent of the systems. Okay, constituent of the systems. Okay, so if there are n number of particles, then there are n number of positions and n number of momentum. If 3D motion is there, then each one is going to have 3 components. So 3 and 3m. They evolve with using in the classical mechanics. They evolve following the Hamilton's equation of motion. Okay, so when we say ergodicity, it simply means these phase points are uniformly starred, not mixed, starred in the entire phase space. Okay, so means that the probability of getting each and every microstate is equal. So equal a priori probability. Okay, equal a priori probability. Otherwise, what happens that if in certain particular part of the region, if you say, for example, in a phase space, you make a block and count the total number of phase points there and divide it by the total number of entire, so you will get the certain probability you can associate. Okay, so if these are not completely starred, okay, then you will not be able to mention about the equal a priori probability situation also. So for equal a priori probabilities, this ergodicity is needed. Ergodic word itself means starred. Starred mathna, जैसे दही मथते हैं ना हम लोग. So you start the entire number of phase points, which are actually the microstates, okay, uniformly.
Yeah. Because I was wondering is the fact that we have
and because of that this ensemble theory works actually. You see, the time averaging becomes equal to the ensemble average. This is how we represent it. Okay, this is how we mathematically represent the ergodicity condition. That is, the time average becomes ensemble average. That's why we leave this time averaging for the experimentalist, and theoretician starts working with the ensemble averaging, knowing that they are going to give the same result. This happens because of the ergodicity.
So I was wondering if the maximum number of microstates and the equal probability of each microstate are two independent or one is to the other. these
What?
conditions.
What?
What condition is that if you include a macrostate which has maximum number of microstates,
Huh.
and the other condition is that all the microstates will be equally accessible.
No, all the microstate from beginning itself are equally created. Okay, so system can go into any kind of a microstate with equal probability. Okay, it is that what kind of particular macrostate, okay, yeah, which are there may be many combinations, okay, which will give rise to a one particular macrostate. It is not that the वो macrostate की probability ज़्यादा है. Each, say for example in this example जो मैंने block बनाया था, each microstate has a probability of 1/16. Each micro has a probability of 1 but the microstate with 2 up and 2 down are happening most of the time. That's why the number of the observable is 0 all the times, and corresponding number of, then I am saying the number of microstates corresponding to that is maximum. So that was a small system. If you go for a bigger system, you see, you will find that it comes out to be it's a peak, delta kind of peak. Okay, so you will find that there's a Gaussian peak, but it's a very, very narrow, very small width. So that what happens, that the number of microstate corresponding to the equilibrium, okay, is maximum, and for any other microstate, even if the temperature is, say for example, equilibrium temperature is 30 degrees centigrade, even 29.9999, if you see the total number of microstates which are associated with that, you will find that they are very, very small in comparison to that, of the order of 10 to power minus 51 order of magnitude. You can find out. Okay, this can be calculated very easily, that a small deviation from the equilibrium, you make a small deviation, okay, you will find that the number of microstates associated with that falls very rapidly. Okay, so for all practical purposes, you can say that all the time system remains in that. Practical purposes, यही benefit है. हाँ, जैसे सिस्टम की साइज बड़ी होगी तभी ये सही होगा. सिस्टम साइज छोटी होगी तो डेविएशन जो फ्लक्चुएशन होगा वो बढ़ जाएगा. Any other question? Ask questions, because if I will not be able to answer, sir is there.
I had the one last thing. So you said for active systems, heated balance is broken even without external drive. But this again is saying for active systems there is some external force that is at age very always. So when we say it breaks even without the external drive.
No, I'm not saying that without external drive. See, I said two things. One, that there is a driven system. Okay, driven systems are those systems which are out of equilibrium because of some external reasons. Okay, some external reasons. Like for example, you take something and stare it. Okay. In the case of active systems, I think Peng will confirm it, that each individual, okay, is taking energy from the surrounding and burning it, okay, because of which it is not in equilibrium. It is showing a pattern motion or something, some kind of movement is happening. Okay, so both are same, but all driven systems is not characterized as a active systems. Active system comes when each and every particles are independent from each other and they consume energy of their own. Okay. So if energy is being supplied, it is supplied at the level of the constituent particles in this particular case. In the case of activators, if energy is there, some sort of energy, the chemical energy, something like that, the energy is being supplied at the individual particle level, not at the bulk level. So when we say the driven system in a larger sense, we saying that we are supplying energy to the rod. ले सबको गर्म कर देते हैं एक साथ, है ना? लेकिन वहाँ ऐसा नहीं है. There, every individual constituent particle is getting. So we are talking about the supply of energy from some means at the individual constituent level uniformly and homogeneously. Okay, so these two things come into picture. Any other question? So if there is no question, then thank you very much.